If this is mesmerizing to you and you're wondering why the heck I have an entire RGB strip flying across the screen for thousands of labs, this is the video for you. So, why am I showing you this right now? So, the whole point of this video is how we can control these labs and use the magical stack inserter for every single type of science. This is a really hard thing to do for a number of reasons I'm going to demonstrate in this video, so stick around and listen to all of that. What we're going to talk about though is I want these inserters to swing exactly when the science drops to 1, and only then, and only be active when those sciences need to be running. I also am doing this with an incredibly complicated way of doing this with this logic. This is needed, I promise you. Regular clocks do not work. I'll explain why that is in this video as well. There's going to be 2 or 3 main objectives this video. 1, I want to get stack inserters to work. I want them to work with stack 16. I do not want them to work with lower values. I don't want them to work with 8 or 12. I want them to pick exactly up the science exactly when they're needed. Because in theory, that is the best for UPS. It is incredibly difficult to do though. I also want this system to be handle every single type of quality combination you can put in there. So you can put epic pink with legendary white and rare yellow and uncommon purple and common the rest, and it should just work. Easier said than done. I've been spending about 3 weeks on this problem, and I think I've got a solution. So the purpose of this video is to 1, explain in general how the whole system works, what are the problems that come from just using basic clocks, and why I've been using bulk inserters up until this time. The second thing that I want to explain is why I have this giant RGB flashing across the screen, and there's a good reason for that, and I'll explain it. 1, yes, it's for style points, but 2, there's a functional reason for it. And then lastly, I want to benchmark this new system that I've created compared to all the other versions that I've created in the past and see how much of improvement this makes. And also, I want to test, right now, I'm running this with quality science, or just all normal science. But what happens if we start putting uncommon science in there, and how much of a UPS gain do we have if we have properly clocked all the inserters? That was a mouthful. Hopefully this stuff interests you. So if you're not interested in the next portion where I can explain all the problems, there's going to be a written version on my GitHub, so you can just read through all that content, and you can skip just the results if you're interested in that. Also, the results are also all included on my GitHub page, so you can just jump to that section if you're also interested, along with the blueprints. I will also include all the blueprints to all the designs I've created in this video, and you can just go and copy those as well. However, I highly recommend you stick around for this next portion, as I'm going to explain this complicated magic that I've created here that actually is finally controlling these labs appropriately. And finally, if you stick around until the end, you get to see me control this with 4,096 labs so that I can run the benchmarks appropriately. So with that, let's get into the video. So I want to explain some of the problems that you have when you have just a simple clock. So in an ideal world, how would you figure out a clock that you want to insert for this science here, right? Well, we know that a inserter can pick something off of the belt, and it takes 8 ticks for it to swing and grab something. So if it's grabbing 2, that'd be 16 ticks. So I've set that up here. That's how often all these are going to run. So there's A through all the way through P. That's going to be all of these inserters here. So there's 32 of them in groups of 2, just so that I can send the same signal. I just have that because that's what I use in my end design. So it basically, you can just treat them as they're all going to run at the same time. Whenever the inserters are active, this little light is going to turn on and we're going to see it. So let's go ahead and just run it. So I'm going to connect this up. And right now, just assume that this clock is perfect. So right now, as we're running railgun shooting speed, what you're going to notice in here is if I look at this, I can see that right now, all these sciences are perfectly synchronized, except for purple. Purple's a little bit off. So is, and orange as well. So, and then again, Promethium, right? So all the ones that are not being consumed are currently off. And it's kind of difficult to simulate this and get it to exactly happen. So I'm going to switch sciences a couple times until I can eventually actually get it to happen. So it's whenever you're switching sciences and you're monitoring effectively, now we're using purple, and you can see that those timings are off. This only happens in like a one-off scenario. So I'll switch a couple times and then I'll skip to that part. So it won't happen all the time, but eventually you'll get into this spot where you are completely desynchronized if you switch at the wrong time to science. And so you're seeing here what's happening is whenever this inserter is active, we'll go ahead and just watch this here. And we'll wait until one of them runs out, so it's going to be pink first, or gray. This is now considered to be active, and what is being shared on gray? So gray and blue here, but the problem is now your purple science is at 21. So why is that an issue? So if we go forward in time here, you're going to see that this inserter here can pick up blue, right? So this runs forward, that's fine because it's under what is considered the threshold. So yellow should be able to be picked up here as well, because this is under 9. So when you're running normal science, other than Promethium, the stack size is 9. But as we go forward here, you're going to see this other inserter can pick up yellow because this is under the limit. However, the one that cannot pick anything up is purple science. So that's kind of an issue because if we go now forward in time, again, we also have the issue here where you're just slightly off by 1, and it's an off by 1 problem where your blue science is now under 10, and this period has come by where it tried to insert something, and the entirety of it was just beyond the rate. So if it's off by 1 in this case, where blue science is not going to be able to be inserted because white science was already inserted, and if out of all of these 12, if there's ever an off by 1 and it misses the whole cycle like this, you can see it got processed. Right now, it could have inserted it, but the sliding window of time based on the timer has passed. So one option to get around this is you could decrease the stack size down to 8 and double the speed. That's still not ideal because you can still run into this situation, but it mitigates it for a good portion of it. But that also means that you're running the inserters twice as often and they're swinging twice as often, and that's not ideal because they're going to resort back to wait lists. This is also even worse when you get into research productivity. So to demonstrate the problem, I'm now running research productivity, but I've reduced the stack size down to 8. And I'm running it actually 4 times as the amount that it actually needs to, just to guarantee that we're inserting something. But right now you're seeing that everything is working. And it's working for a very specific reason. Because when you go to research productivity, the labs no longer insert and allow something to insert when you're under 25, or under 9 rather, in the automated insertion limit. It's now at 5. So this becomes a problem so that right now you can see here, I just wound up changing this now to stack 16, and this is still fine. But we're also running it way faster, and so you're seeing all the pulses of the wake list, so that's not ideal. So to get around it, and let's just set it back to the normal speed, if you're looking at this now, you're seeing that this is now more further exasperated, because if you look at blue and purple here, they're actually only off by about 9 or so, I think, here, but or even 6 in this case. But they're going to still have that problem that didn't happen before in the other science, because now they can only insert when it's 5. So this is actually 4 times as bad because you're not oscillating around the halfway point of a stack size for an inserter. You're now optimizing and trying to hit a quarter of it. So I've developed a solution that's going to work to handle all the edge cases we just talked about. Before we go into the weeds, I want to start off real high level. So the first part of this whole system is, let's say we'll ignore all the complications here on the right, and we'll just talk about just this left section. So for the left section, what is it doing? Well, it's taking and monitoring one lab. You can see that here with the wake list conditions. This is the only one that's currently active. The rest of all of these other 63 labs here are all following the signal of that one lab, and they're all inserting whenever they are scheduled to go and run. So for this demo here, I have uncommon science for white science. This could be any quality, but I'm just demonstrating it here with uncommon. And I have normal science for everything else. So what this is going to do here is I've set on the lead. It's monitoring it. And every single time a normal science should be inserted, we should at least see a science get inserted here. And what this does is it normalizes it so that we can see all the different sciences here. And so if we switch, let's say, to laser weapon damage, you'll see that, okay, this comes in, the system will clear its memory, it'll reduce the stack size on all the other inserters, that's that little yellow, And it will then rely on wake lists to synchronize all the sciences. So you're seeing that happening right now. So what's happening here is it's now recording and starting over whenever a new science enters for a long enough period of time. So that is 2 frame cycles. So now it's going to record it. It continues to just handle all those values and holds it in here. Now, this will now, after I think it's 6 cycles, it will now go back to, instead of using wake lists, it'll go back to using the normal timers. And the whole reason that that works is that during a transition, when let's say I go and I bring in low density structures, which hasn't been run in a while, you're going to see that by detecting it, resetting the clock, going back to only monitoring now this orange science, we're going to wait, reduce the stack size, and what this is allowing this to do is to slowly drain or get the science so that it's within at least 1 or 2 science of each other. And that's great because then that gives us enough time later on to not have to deal with the fact that these are off by 1 or off by 2. So this is enough so that it can completely drain, and once it drains for 1 frame, when it goes back to the regular clock, all the science that's in there is at least under 8, which is the trigger condition to allow you to insert more science. So you can see that this one didn't run out, and so whenever it happens to get inserted, these are at 16 and this one's at 20, but that's fine because it's under the 8 threshold that we needed, or the 9 threshold we needed to be in. So this works if you're switching between all the different sciences that are not going to be research productivity. Because you can't, with a stack size of 4, you can't get that range to be under 5, guaranteed. So when we do research productivity, it's a very different story. So when I switch to research productivity, you're going to see a kind of a fun thing happen. We're going to detect research productivity for this first cycle here. And we are going to go into immediately, we're going to go into this mode of trying to handle and hold all of this science here. So we're immediately switching the stack size, and we're draining it now to the point where everything is at least at the minimum value that it can be, so somewhere under 8, right? And then the clock is going to slow down. We're going to have a brief period here where we pause. We send no more signals to all the inserters. They cannot insert anything anymore. And this allows then this to drain effectively. And then after that, we're going to have a trashing period where this is going to trash anything that it sees in the labs, and there's a signal being sent to that. So we'll just watch this one here unload. You're seeing it completely remove all the science from it. It does that across all of them except for the lead. And all the sciences then are completely removed, go on this waste bucket, or this waste line, which is the same as the normal spoilage line that would exist. And then this will get all the way, and just right now I'm just putting it on an infinity loader that'll just take them out. But in an actual setup, the way that this would work is you're going to have probably a recycler, and you need a recycler because you'll see that to basically recycle them down to nothing or insert them into another lab. And that's important because these science packs will be at different used values, and they won't be and they will mess up your timers later if they're at, like, let's say 50% utilization, and then it will screw up your whole system. So you can't just directly use them, so unfortunately you have to destroy them. But by draining the labs to the smallest amount that they can possibly be, you're gonna not void as much science this way. So that's effectively how this system works. And then once it's drained all the labs, it's now good. You're gonna notice that the clock is a lot slower running Promethium, and that's because we're now going at half the rate. So we're gonna have to speed this up for this transition to happen, and it already did. Great. So we look at monitors, the actual wake lists. You're gonna see that agriculture science is running more often than the rest of them, and that's just mainly because you can adjust this timer here. This is at half the sample rate of your normal science, and I will explain this timer here in a second. But what this basically then does is I decided to just run faster than needed to just guarantee that we're always going to get agriculture science in here regardless of the freshness that's in there. So if you have higher freshness, you could probably decrease this so that it only runs a little bit less often, but I'm handling the case where it's like 25% freshness, so like really, really bad. So overshooting it for sure, but that is at least the concept. So anyway, so now all the labs are synchronized, all the science is exactly synchronized, and you can just slowly just continue to now run at Promethium science rate. Now the only downside is if I switch to another science afterwards, I don't have that nice little quick reset because I have to wait until everything is completely removed. So that means that you're gonna run at half rate for at least 14 of these cycles. So what that actually winds up being is 14 times 259 ticks. So that means for about 1 minute, you're gonna be running at half the rate on your labs. So you could, there's a lot of things you could do if that transition is annoying for you, but for most of the sciences that are going to take for me 24 hours plus to run, I don't care about 1 minute of running at 50%. So that is now going to run here for all these sciences. They're going to now reset, and now they're just going to reset and go back to their normal cadence because Promethium is no longer detected, and now we're at the faster rate. And then your transitions still work like normal. And also, the cool part is because the transitions are done in such a way where all of them are active, all the inserters are active, you actually see all of them turn on, which means you're handling a transition, which is kind of cool. So, and then the moment that they come out of that transition, it goes back into a normal RGB wave. So why is there an RGB wave? Let me explain that real quick. All the inserters are offset. They're offset by 6 ticks in between, in pairs of 2. And I did that because in agriculture science is about 128 ticks for it to run. And it winds up then basically every 128 ticks, I need to be able to run 32 labs. So I just divided it by 2, so I have pairs of 16, and then I added 16 ticks in between with 24 ticks for each of these individuals to ones to run, and that's basically the maximum that I could do to get all of them to be spaced evenly apart like this. And the reason I'm doing that, I'll explain that over here, is because I have found through testing that the more spacing you have and offsets you have, the better your UPS is going to be. And the reason for that, so I saw a 6% improvement on a test that I was doing compared to just running all of them at the same time. So for this test that I ran, there's 15 inserters pulling off 240 items per second, and they run every 120 ticks, and then they can all pick up exactly 16 items every single time. That's how the math works out. You can read more about it if you're interested in it. But I created different setups, one that ran all of the inserters at the same time. There's 50,000 inserters here, just so you can understand that. 16 columns, 92 rows of these. So I set up different ones, one where I had an offset, 1 tick offset in between. Whenever you add a combinator and you have one signal network going into the next one, there's 1 tick for it to evaluate it, and the next tick it propagates it. So it'd be off by 1 tick. So just naturally it will increase that. I also tried it with having separate clocks. Even though the clocks were all synchronized, so I paused the game, put them all in at the same time, started them up. But just to check, like, is it better just to have more networks or not? And rather than, like, so the signal doesn't have to propagate to all the entities. And then I had one also with, 16 individual clocks, so 16 individual networks, but then just offsetting each of the inserters by 92 ticks. And that was the best result. So you can see here just by the max MS time how much drastically it reduces it by when you just start offsetting your inserters by a value. Just like even if it's just 1 tick, it makes a huge difference to the max millisecond time that you're having. So that is because when you have 50,000 inserters all activating at the same time, that's a lot for the game to process at once. So even though the average is really similar, you can start seeing that, like, because you lower the amount that that you have to do in one cycle, your overall UPS actually goes up. So it's good to spread out the inserters. So for that reason, that was like having 92 ticks in between all the inserters actually activating was good. So in my example, going back to Factorio Land, I don't have that many inserters, but I do have I wanted to create a module that is all of these inserters here. And I wanted it so that there are going to be 32 inserters. So those 32 I divide by 16, and then, yeah, they are offset by 6 ticks. The ideal value would be 8 ticks, because then to minimize the transport line time between inserter to inserter, because they can fully get filled up. but 6 ticks is enough to work also within my agriculture clock time. So that's what I have decided on for this particular design. Anyway, that is an overview of how this whole crazy system works. So let's dive a little bit more into the details of how I got it to work. So to start breaking down how this whole system works is I first need to explain the universal clock that I've created. So the way this works is you're going to see here for demonstration purposes how often these clocks reset. So in an ideal world, normal science here should run every 259 ticks, and I know that because if I look at it with the rate calculator here, you can see that the consumption rate is 3.704, is how much science it's consuming every second, so every 60 ticks. So if you just basically said, okay, well, I know that my inserter is going to swing and grab 16 items every single time, so you divide that by the rate, and you multiply that by 60, so that's to every 259 ticks, and some fraction. So that's kind of a problem because that means that you can't just set up a normal clock that just counts up to 259, and you wouldn't know, like, do I count to 259, do I count to 260, and then do I reset per tick? The answer is you just don't care. What you can do is you can use this exact same thing that we have here, and you can plug it into a tool like Wolfram Alpha here. And what's nice about that is that will give you now an exact fraction that's shown on the bottom there that now highlights exactly like what a ratio is in a regular fraction form. So it's really nice because now you have an integer, the 1, 2, 3, 4, etc., that we'll be able to now that we can exactly count up to. So if we had a clock, and how would you set up a clock like this? Well, let's go back to Factorio and explain that. So the way that it would work here is if you have now those two values that we had, so let's start with the normal science consumption of 120. You see that I've plugged this in here. This is 120,000 is the number. So the way that this works then is I feed this into this clock, and this clock is going to count up by that denominator. So 463. So that means that every single time that this value, or the clock, is greater than a modulus of 120,000, it's going to reset. So we see that in the next step here. So whenever what I do is that I don't have to have basically 10 different, or rather exactly, instead of me having a combinator for this one, this one, this one, this one, so all 6, I can just use the each operator here, so that I can just take the modulus of each value and just output them here. So you'll see that the counters here for uncommon is resetting at every second time that the normal clock gets reset, and so forth. And so this constantly shifts. And then legendary is the last example that will reset every 6 times the normal science will go. And agriculture science is running at twice the rate of uncommon, or rather, sorry, of normal speed. So the way that then this works is, just for this demonstration purpose, I have gone and set up and recomputed this back into ticks, so you can see how long these are active for. And I've also set up these nice percentage bars so that you can see exactly when these different timers are activating, and when exactly they reset is that little blue light. So you can see that like sometimes it's off by 1, sometimes it's off like a little bit extra, and so you'll see that these ticks are slightly off occasionally when they're running, but that's okay because, like we said, when you look at this example here, sometimes it's going to be every 259 ticks and every 260, sometimes every 259, sometimes, and so it'll just round up and down, and will go up and down from this number. So you'll be sometimes there, sometimes not. So in practice, this really is 258 ticks of total time that it's running, but the point is like it'll be on 1 tick, off 1 tick, and that's okay. That's kind of how this one works, so that it's compensating for the fact that it has a fractional equivalent, and it smooths that out over time. Okay, so that's the subtick clock. So what you can see then here, if I pause this, is you'll see that the ticks here are going up consistently, but the length of time and the number of ticks that the legendary is waiting here is significantly higher than, let's say, your agriculture clock. So if we go forward, and I go 1 tick at a time here forward, you're going to see that this will wrap around right when agriculture gets to 100%, or that's at 128 ticks in practice. So you might get to 129 and reset, sometimes it's 128, etc. So that means that you have a total of 128 ticks for agriculture science, which is kind of how I'm running the whole system. I'm just running it at twice the rate for agriculture, just in case you have like 50% of freshness, for example. So just to compensate for that. And so normal science will wait until we get to that magic 259 number. And let me see if I can catch it. And we'll get up to 100 and okay, stop. Perfect. Good timing. So 258, you saw it reset that time, right? So that's where I'm saying sometimes it's 259. So let's see the next time it comes around. So 255, so we'll go one tick forward, 257, 258, and it got reset. And eventually at some point it'll be 259 where it gets reset like that. So that is kind of how these clocks work, and then each one's just a multiple of that. And so you're seeing that this one gets reset at 3 times that amount, this one gets reset every 4 times, and this one every 5 times. So they don't always align, so the way that what you really want is the case where all of them happen to coincide exactly the same time, which you're about to see here. So this is the case where all the clocks exactly synchronize, and they hit their final number here, where they all get to 100% at the same time. This is the case where you want to reset your overall global timer. So that's how I've done this here. So I've done it at twice the amount, just for my own, like there's no reason not to. But it's because I also want to have that case where they all have the chance to have the 128 happen and the 129 that you're seeing here. So they always have that extra tick. So the global timer itself basically says I take effectively the least common multiple of all of these, which is 12, and then I multiply it by 2, and I multiply that by the base of 120k, and that just makes sure that when on the wraparound condition, it's always going to have this 9, and it has its 8 for all of them. And that's effectively how this clock winds up working. So this clock is now something that we use to now store memory for the entire system. So to break this down, the way that this now works is like we have that lead that I explained before where it's monitoring everything that's in the inserters. They're set to a stack size of 4, and that's just so that I have the highest sample period as possible. And that makes it so I don't have to do things like account for quality and multiplying the numbers and trying to smooth things out. And so it just means that even at all the way at legendary, which I'm happening to be running here, it still has a chance to grab it. So if I switch to, let's say, worker robot speed so that we can see it, you're going to see that this is a memory bank that holds the values over time. And you'll see that, okay, legendary wasn't counted for that cycle, but it should be counted for this one. So it'll be basically every 2 it will swing for every 1 normal. So basically that means that this one swung for all of these. This is going to be 12 times, and this is only going to be 2 times. And so then that means that over time, as you run this memory bank is going to hold all those values, and it will shift ever so slightly, but it means that you have a guarantee that you're at least going to have like basically the 8 that you're seeing in here. So that's convenient because now we have the ability, as we switch sciences and we switch to something else, you're going to see those values come in and slowly get erased from right to left. So this acts like a shift register. The way that this works is every single time it sees a normal quality signal, and that's working now with the clock that we talked about. But this, whenever it happens to be less than 463, that means we've reset the clock, and then we just record it for a pulse. So it's 1 tick where we happen to see the normal quality. Then it increases the index, and the index is the recording here, the sample. And it then just has a window where it's recording something, and every single time it comes in, this all just handles the reset condition and allows it to reset what it was recording for that sample. Nice thing about this is that you can infinitely stack this to the right or the left just to have even more memory. I've chosen to have 14 slots, and that's mainly just so that I have a guarantee for legendary to have at least an even distribution of legendary throughout the whole thing to make it easier. Why is this nice? So this is nice because now I'm not thinking about things in terms of ticks. I've abstracted it, and now I'm just thinking about the number of times I've seen this science, which is a lot easier to reason about. And it also means that I can dynamically change the sample period. Instead of at normal, I could do uncommon, for example. And now this clock would slow down and do twice the rate. And that's also convenient because now you guarantee at stack 16, for example, that legendary is going to appear in every single slot. So that's also a choice that you could make to do this, but I've opted to just, for this entire thing, to always go normal rate, just so that the system's a little bit faster at cycling through all of these. But, and then just accounting for the fact that I'm not going to see legendary quite as often, and that's okay. So cool, so now we have a memory bank. So the next thing that I wanted to do to improve the system was create a leading edge detection. So whenever a new science is introduced, like let's say low density structures here, the second time it is seen, so whenever this now is reset, it's about to remove all these extra sciences, and whenever the orange science is about to come in, what I say is, hey, I've seen these sciences for 14 frames at least, and then this one's coming in now for the new one. So it's greater than 6 in this case, it's just a number. And then whenever I see orange science now for the second time, that means it's been just introduced to the system. Either you ran out of it, or you wound up just transitioning to it, most likely it's a transition. Then in that case, the moment that this gets to 2, I want it to go and perform for 1 tick a trash bin icon, and I want it to wipe the memory, which you just saw. That's nice because that means that now it's going to start counting up the whole system, and it's going to count up with including the original science that was there. This is now just going to basically count up until it's just constantly running at full capacity. The moment that you then switch, it immediately wipes the memory and restarts over again. And so we can see that here, every single time this is running, this switches over, and then it will, after, the only difference that it doesn't happen is if you're switching to the same science. So if you're switching to the same science, and you have a subset of it, so you can see like purple, blue, green, and red all run within what was currently, like previously was running, which was worker robot speed, then it won't trigger the condition until it gets to the very end, and then it resets it. That's not ideal, so I could probably be a little bit more risky and set this at a higher value so that by the time it gets to that value, like it's just, there's not a good way to prevent the trailing edge from happening, but it's just a side effect that once this gets down to 2, it resets it. That's okay. Like I've dealt with it, that's the only case that it doesn't handle is when you transition back, because like ideally you could just keep the same inserters active the whole time. But the main thing that this prevents is you having to resynchronize the science in the labs twice. Once when it introduces the science and once when it removes it. So this guarantees that it's always going to try to synchronize it, even if it doesn't need to, like when it's a subset. But at least when you transition immediately to a new science, it'll immediately trigger, hey, I need to go and resynchronize in the labs. The one last edge case that exists with leading edge that I had in testing and actually makes sense is there's the case where you're about to spoil the agriculture science because we're not running something that actually requires agriculture science. And that'll just happen in the lab because you're not ever, these are always going to be active and inserting things into the lab. So the way that I handle this is I read the hand contents of the spoilage, and that's the only thing that I take out of the lead lab. And so whenever, and we'll show this here, whenever this happens to get to a point where it actually actively spoils, so right here, spoilage happened, right? This converted into spoilage. This inserter is now going to pick things up, and it is now going to send a pulse across this wire that is going to send now a signal in here, and we're going to record that spoilage was detected for a second. So what that means is now we have spoilage in the system, but that also means that we had a secondary swing that happened just now of this inserter, which is actively moving, that just put some more agriculture science packs in there. And that's a problem because now we have a single frame here where we detected agriculture science. So to prevent this from propagating down in here, you're seeing that I'm filtering out that signal altogether. The way that I do that is I just say, hey, anytime I detect spoilage, I'm going to multiply that by -1. So that's just going to remove it. The next one I'm doing is also, I'm just multiplying agriculture science by -1 always. Both of these feed here, and I'll show, I can't show visualization while I'm paused, but that's fine. So both of these two here are going to feed into this arithmetic combinator, which is just going to multiply things by 1. So it just takes all the inputs here, and this is just to delay it by 1 tick so that these can both feed into the front and subtract it. And then finally, I just re-add back agriculture science only if spoilage is 0. So this takes now a while for this to completely cycle through, and you'll see that right now, sure, I happen to have this one agriculture science that's present, but it's getting filtered out completely and all downstream consumers don't see it while agriculture science or while spoilage was detected for a frame. And also in practice, when you're actually running agriculture science, you're not going to see spoilage ever come out of the lead lab because effectively it should always have the freshest science compared to all the rest of the sciences, and also it's being actively consumed. So this allows you to handle this edge case and not cause an early reset, and also not cause anything else to think that there's actually agriculture science that's in the mix. So now that we have discussed this portion that's here, let's go ahead and talk about the next part, which is detecting Promethium. So now we have values that we can monitor, so we can see all the different values of the cycles that we have. So what I do is now, okay, when Promethium science is detected and it's coming in for 1 frame, I'm gonna wait for a second. And the reason this is because I don't want, like, let's say all your agriculture science ran out because, you know, maybe you're buffering it or whatever the reason is. I don't want this to slow down the clock prematurely. So I wait until at least 3 cycles we've seen at our normal speed. So basically at twice the speed, I've seen agriculture science inserted twice. And the moment that that happens, then I wind up saying, okay, cool. Now Promethium is here. So it triggers this little purple icon, and then that comes into here. And then what I do is I just take all the values from the base clock, which is this one, and I just add it again into the network. And so since when you combine 2 different signals together, now you're going to see that instead of every 720,000, this is now running at every 1.4 million. So, and that's the same for everything. So everything just all of a sudden got twice this, basically like half the rate. So half as often as those clocks are going to actually get activated. That also means that the sample period, nicely all combined together, is also going to be half the rate. So now the sampling is happening exactly in line with the normal quality of Promethium science. So now this is recording, instead of the normal rate, this is now recording at the Promethium science rate. And so you'll then see here that over time, this will completely hold all the values for Promethium. The only edge case that I have removed from this is that if for some reason I wind up saying that I've got laser weapon damage that I'm running, like let's say I switch to this, I do wait until the entire thing is completely removed before I trigger basically a memory reset. And actually I don't even perform a memory reset. That's actually mainly what I wanted to talk about. I don't do a memory reset for Promethium, and that's because with the voiding of the science that I'm doing, I know that all of the values for the science are already going to be at the exact same ratios because they all were thrown in at the same time. So I just handled that case. So that's Promethium science and how that transition works. So next part is we actually have to send values to the labs. So let me explain how this is currently work. We have red and green wires that come across here and they send signals to this. This whole setup here is going to be, each one of these are going to be connected to a inserter. And the way that that actually looks like in practice is you happen to have here all these inserters, and if you look at this with the wires here, the red and green correspond to this one, the blue and purple correspond to this one, and that's why I have set up all these individual channels so that they can route to each of the individual inserters. Okay, so if you're still with me, the way that this works is you now have a signal that is red and green. You're going to notice that here I have set, this is white science, but it's not showing up as uncommon in my specific scenario here. What I'm actually showing this as is I have an uncommon signal. And that's because we are going to be sending we're going to hold a value and send uncommon while it's during its period when it needs to be on. And only then will it send for that particular split belt all the signals that we send to all the inserters. So it cycles through them and steps one at a time, right? So how does this really work? The way that this works is if we are not in a place where we're going to dump the science, we're going to send a normal quality, and that's an abstraction so that the downstream clients don't care if they happen to be running legendary, or in the case before, uncommon. All that they have to do is just say, cool, lead has to have the same quality the whole time, and then the downstream ones, all you wind up setting is in here, cool, I'm running legendary and white space science. You never have to touch this one, you only care about this one. That way you could have a row that's rare, a row that's epic, etc. And then you can just follow the lead lab still. All you're just caring about is which science is currently running for the research you're doing. So you're seeing here that we're cycling through all of them. So you're seeing normal right now, comes off, You can see normal and at least uncommon, so that one's on. And you're seeing legendary isn't active until eventually legendary actually shows up again. So what would that look like? So we wait until probably this transition here. Now legendary is here. Cool. It will know that I need to insert space science. So that's also convenient because cryogenic science is not running right now, so it would never need to activate the inserter for that period of time. So that's how this one works. So then how does it actually go and decide on all those things? Well, we basically just have a memory of all the science, and I'm going to wipe this for a second because I think I just reset and add white science. Cool, great. So this holds all the science that has ever been inserted into the lead lab with respect to their quality. So this actually holds the quality value. And as you insert different sciences, so if I would switch to, let's say, purple science, it will go and realize, okay, purple science was here, it'll hold that value. And even if you switch to going to another science, so I go to one that doesn't consume it, it still just holds this value forever. And it will just remember that you happen to use this at some point in the lead lab. So why that matters is because when you're normally running it, we send that normalized signal across everything. And then we wind up, when we transition to Promethium science, for example, we have a very specific thing that happens. So that whole thing, when we trash effectively them, what's going to happen is we're going to have one pulse where we're going to wind up basically blocking all the science. And when it's blocked, that means here, even though we're having these signals for the sciences that were running before, these cannot get those values. So they actually, during the block period, they stop outputting anything. So that means that they cannot get the signal for activating the normal, and they can't get the automation science pack signal. So then all the inserters here downstream do not activate. However, the moment that we switch to Promethium, what you're going to see now is we have blocked all the normalized signals, but now we're sending all the values, including their quality. And that goes into these selector combinators that are just outputting a random value every 2 ticks. So to demonstrate that, let's go up here because I know it's going to be happening on this lab as well. This has already dumped the science because I went a little bit too fast, but you'll see this value now fluctuating between all of them. And that's how this handles, like, hey, these are any of the sciences I've ever seen inserted in here. And you're seeing that you're going to have like that white science that comes in that's uncommon for a second. And so this can just basically output everything and drain the lab. Once that period of drainage is done, let's come back to, where is my example here? Fantastic. So when this happens now, all those clients downstream are going to wait until the full trashing period is done. So that takes 1800 ticks, which I've just decided because it's longer than legendary. And I don't know, you could change this, optimizing it. This works right now. So then it will go back to using the normal quality signals again. And then all of these can go and start going back to their normal schedules. And now it's also using the slower rate of the Promethium science if you are running Promethium. So that is effectively how this whole system works in order to handle the transition. The only difference is that, one thing just to note, this system here, it just, whenever the ghost signal happens, and this is just on a base interval, it's going to call a little reset, but it'll pass all the values in here. So you'll see then here kind of, if you happen to have normal, uncommon, and pink, it just holds those, and then that tells you, hey, you're currently in this period. Go and send values to inserters, right? So if you're normal, send it to normal. And this works because, again, and it's really important to understand with combinators, each combinator delays it by 1 tick. So for the first tick, it'll see both the values, and it will call a reset in here whenever the ghost icon comes up. The second tick, it will grab all the values that come in. And then on the second tick here, this will also get reset. And then the third tick, it'll grab the values that it just saw and shoves them back into this combinator. So that way you're always holding the value until the reset occurs, and you constantly can continue to send the signals downstream. Cool. If you're not lost yet, one last thing to explain is whenever we happen to have a transition that is detected and anything is less than 7, that is when we're going to send a separate signal. We're always going to just keep everything active. So this sends all the signals at once. and it reduces the stack size to 12. That was that whole flickering thing you saw earlier. That makes it so that all the inserters are active constantly, and they're running at only stack size of 4 to kind of synchronize them. And this happens no matter what transition you have. If you happen to go and you switch over to laser weapon damage, you're going to see that this resets. I guess I was running Promethium Science. We'll wait for a second, and let's switch over to steel. And let's switch back over here again. So this happens. You're going to see this alert icon comes up. All of them are active until effectively then this transition period goes over, the alert goes away, and then everything goes back to stack 16. All right, so that's how I handle the transitions and the synchronizing and all of those things. Next, let's get into how do we schedule the inserter swings to be staggered. The next bit I wanted to demonstrate, we've already shown the client and how it works. What I wanted to show is how this staggering effect works. So you're seeing here right now we're running laser weapon damage, so we're only running the blue, red, yellow, and then the gray compound, basically the gray ones. So all these inserters are actually exactly how the other inserters would work, but I'm just showing it here. So the way that it works is we're going to send some values. So each of these are going to be A, this one's B, and this one's C. And they're also going to get a stack size whenever it happens to be active. And then it turns on and turns off. So what happens then here is that you're going to notice in here a whole bunch of letters kind of come through every single time this is active. So only when both of these are in their current period of normal science consumption, you're going to see all those letters come through. And so for white, because it's legendary, it's going to happen a lot less frequently, right? You just saw it there. So you're going to see basically if we increase this in speed, you're going to see this is only going to run occasionally. And when it happens to hit its current period where it actually happens to need legendary, it's going to also run at the exact same cadence and spread everything out. So hopefully I could show that here. There you go. So there is the legendary. They all were synchronized. So how does this all work? So behind the scenes, what's happening is, okay, we've taken the concepts, we've explained everything up until this point. We are now at this last step. So the last step that I do is every single time that the reset happens, I'm going to start a clock, and just for fun, I've called this a stack inserter. This is an inserter that's going to go up every 128 ticks, and that's what we showed with the clocks originally, because this is getting reset every single time agriculture science runs. And so what's happening then is these are going to feed into, and bear with me, these are very specific numbers that I have created, but really what this just means is, hey, 6 ticks later, I want you to start. 6 ticks later, I want you to start. 6 ticks later, I want you to start. And what this does is this is going to feed, and it's going to look at the stack inserter clock, and it's going to subtract all the values here. And you can see this if I slow this down. You can see this slowly increasing to be higher and higher than those other values. So what this really means is on the output here, you can see A becomes negative over time, B becomes negative over time, etc., right? So like slowly this number comes down. So what that means is then on the output, we just say, hey, anything, in my case, I only wanted to enable it for 20 ticks. I want you to just have those values kind of slowly floating through, and effectively then whenever it's less than 20 or greater than 0, I want you to activate. So that means for 20 ticks, we can now control this. We can go and say, hey, go and enable each of these inserters. So that is kind of how that value is working, and it floats through, and then it will basically adjust the stack size as well on transition, and will handle then basically sending all these values to it. So that's kind of how these stack inserters then are controlled and offset. So if you wanted them all to be the same, all you'd have to do is just set all these to be exactly equal. So I didn't create that, but no, basically by hand. Because I was messing around with different timings and different offsets, so I just created a quick script to generate a blueprint for me. So that's kind of actually how I created that, which is pretty cool. I'll have this on my GitHub and you can look at it, and you can just go find it. It's under simulators, and then under the source blueprint, there's this constant combinator offset generator if you want to grab it. The way this works is it generates a little file that you can grab and you can copy it. And then if you go back over to Factorial Land, and we wind up showing that, The way that this works then is you copy that blueprint string, you can paste it in, and now we have the actual timing values. So you see here, this is actually probably the correct one because in my demo, I have 24 as the starting value. So I can just go and copy and paste that in there. And now instead of it waiting an additional 4 ticks to start the first inserter, it'll now just wait and start at 20. So it immediately will start. So in my demo, it was wrong, but that's actually how you could go and correct it yourself. Anyway, that's just how I create the numbers because I cannot be bothered to enter this like basically 16 different times and change the values. So finally, all we need is just a timer that every 10 minutes, we're gonna basically just check if there happens to be spoilage in the labs. And the way that this works is it just winds up basically every 10 minutes for 120 ticks, it's gonna send a spoilage value. That value is gonna come across on the green wire. That green wire is then going to basically go and propagate anything that's in there as long as the denial list is not sent. And then that comes into the decider combinator that's going to send effectively as long as it sees spoilage, it's going to continue to send spoilage. And it will just send a signal to all of the inserters that wind up dumping everything. So that's the same wire that's set here. This is not staggered, it just runs immediately, but it only runs every 30 minutes, so that's completely fine. So these all run. Then finally, the only other thing that I did is I just made this a whole bunch more compact. So I took this whole thing and I've made it a lot more compact so it's easier to copy and paste. But this is the breakout version so you can kind of understand it. This is the more compact version. So you can optionally include the debugger if you want it. So by default, the blueprint is going to be effectively you're going to have a controller you can place down somewhere. And then if you want to go and add the debugger, cool, you can do that if you're just curious about monitoring it. I won't be using this portion, but this will still have all the nice display values. So to demonstrate how this blueprint book works, what you wind up doing is you grab the lead and you wind up pasting it somewhere, like this. And then what you wind up doing is by default, what I'm going to have is I'm always going to have a requester chest for the first 4 that are going to insert effectively the agriculture science packs so that way they substitute for the rest of them. I'm doing that because of the freshness quality on my base, but if you have higher freshness, you can remove these inserters here, and or if you have lower freshness, you can add more. So to add more, the way that this would work, and this is important, that this section is effectively A, this section is B, and this section is C, and so on. So you can also see that by just clicking any of the inserters, you see this one's C. What you do is you grab this agriculture substitute. It can only fit in one spot, so we can put it here, and then you just select the signal C. And then that will set them all up, and then it will automatically turn this one to use the filters to be off so that it doesn't grab any time that this comes in, it doesn't grab agriculture science packs to screw everything up. And if you ever need to undo it, you can just delete these two and then just remove this filter condition. And if you want to be more OCD about it, you can do that and remove it. That's how you undo it. So just an easy way. If you want to completely, absolutely substitute all of them, you just have to painstakingly go through and add them all, but that's it. So the next thing that I want to do is by default, all the followers are all going to be set up to be normal quality. So you can choose a different quality that you're going to be using. So if you do this here, and the thing that I'm going to make sure that I have disconnected, I think I already talked about, is removing that red wire. So the reason why I do not have it by default this red wire connected is because if you're running research, then you're going to prematurely insert everything into labs and you may not want that. So the easiest way then what I would do is we'll connect that wire afterwards, but let's go ahead and set up all the sciences that we're going to need. So we're gonna have legendary in here. I don't know, let's do uncommon there. Paste that over, paste that over, paste that over. Cool. So then now we just have to set up a little bit of a different timing on the white signs. You can still keep them all normal, but you're going to make an optimization by only swinging when you actually need it, because like if you have higher quality, you're going to benefit even more from this system. So if we do this, we can now go and say, hey, we're going to grab legendary from here. That's what I care about. And right now, the reason the extra signals are being sent is because it's thinking there's a transition because it just saw science for the first time. So if you're really curious about it, you can add the controller debugger and you can see just exactly what is going on. Just make sure you copy it on the right ones. As you can see right now, I thought there was a transition, so it's grabbing these sciences and is restarting the clock and starting over. So, and it's basically monitoring these, and then we'll continue to progress forward and it will keep on recording, right? So It's seeing that it actually can't grab anything right now because we don't have any of the sciences yet for steel plate productivity. So that's why just easier. Don't connect this initially. Just wait until you have run all the labs to it and then just connect it. So, okay, so we've got legendary and this is going to be uncommon, which we said. Great, so that's done. The next part, let's go roll over to the other side, and I always input everything from the back because everything like these sciences should just come from novice. So if you don't import them from novice, I'm sorry, you're gonna have to figure out a way to reverse this. I am not going to do that. So for me, I always run uncommon for all of these. So I'm just gonna go ahead and select this as uncommon, and I'm gonna grab this one as uncommon as well. And we will copy and paste that over. And then additionally, just for fun, I'm gonna make this one epic, and I'm gonna make, or rather rare, and make this one rare. And then I will keep, just for the simplicity, let's just keep these, let's have them mixed. So we'll make this one legendary, and this one, oh no, epic, just to make it weird. So paste that over. So I'm gonna copy these real quick just so I can remember it. And then we'll come over here. So we've got to go modify our yellow and gray. So that's this one. So if you run the sciences on a different belt, just change the inputs for each of them. And you can just see basically which inserters they're all corresponding to, and just corresponded with that one. So I have it preset up for the way that I like to run the sciences, but you can choose to run it a different way, and that's fine. So let's do red and green. So red and green are both going to follow the uncommon signal because they're both uncommon. And then what we're going to do is for blue and for purple, so let's grab the blue one. These are both going to be rare, rare, great. And then finally, let's go and do the weird one that we did, which was somehow legendary, gray, and epic, yellow. So you can see here, nothing's connected yet. None of these inserters are here. This is now running. And we can now see that we've had a period of stability where everything's running. So we're going to wait for the wait list kind of condition to happen, and we can just wait until this has recorded enough values. And you can see that it prevented it resetting because the first time it inserted was just 1, so that's good as well. So now we're in a stable point. This yellow light has gone away, we're ready to go, and then all you do is you just connect this up. Now all these downstream inserters will just run exactly in time for when they're needed. Now we can monitor it, that it's actually doing what it's supposed to do by pressing F5, or if it happens to be dark, you can also check it out this way, that it's running when it's supposed to. And we can go and switch researches. You can see that the moment that it detects the new researches there, it's going to have all these active for a little bit, and all the lights turn on. So that means, good, we've detected a transition really well. All of them default to wake lists exactly like they're supposed to. Fantastic. So then, now, that's basically how this is now working, and then we wait until the transition period is over, so we'll wait a little bit. And then, great. Now everything is fully in line, and let's check that they're actually actively consuming everything. Gray should exactly activate right at the end when it's done, and so should the other ones. So there it is. It ran. Great. Oh, and white science, come on. Yes. Good. Just in time. So that is how now this whole system works for scheduling everything and handling the transitions, and also handling the different types of quality sciences. So you can mix anything you want in them. Okie dokie. So now if you want to add more labs, well, that's super easy. You just grab the lead, or not the lead, you grab the follower, and you paste it somewhere in next to it. So we can do this. Now, we could feed this other qualities, and this will also work with it. I'm just, for the demo purposes, because I am lazy, I am just going to, you know what? No, let's do this properly. Let's just really demonstrate how this whole thing works. If I have normal science completely on here, now notice I don't have green wires and red wires connected here yet. So we're gonna have to connect it up on the client. So now we're going to do the same thing down here. So let's say for these, I just happen to only run normal science for some reason. So we'll go ahead and run this. We'll wait until these completely fill up, and that's just a good thing, just to have back pressure on the whole system. Great. These are all connected. So now these should all be only when normal science is ready to go. Cool. And we'll connect this one up. And then we'll connect this one up. And then now, there we go. they should also just work right away out of the box because we've normalized the science inputs. That's the reason I did it, was just so that you can do this. And you can see it didn't insert any of the other sciences that are in here, like this one is, because we haven't switched to research that requires it yet. So, and it's also going to look a little weird because these inserters should effectively be running at half the rate for this bottom one because, well, red and green science, I think they're supposed to be uncommon for this one, and the other one, it is normal. So you're going to see kind of an offset pulse, so you should see, funny enough, it'll actually represent exactly when they're running. So this one should run only when the other one isn't, so yeah, you can see that now. Because red and green were uncommon, so you're going to see basically a pattern where they're both happen to be together, like this one. And then you're going to see a pattern where just the bottom one is now running, and that's it. So now they're all synchronized, and they work great. Fantastic. And then let's just make sure the transitions work, even with this mixed quality. I've also not tested this, by the way. This is just in theory. So everything is handling a transition. It resets the clock. Transition is happening. All the wake lists are active. Fantastic. We'll wait until this is all done. And now they'll all synchronize again. And let's just press F5 to make sure that all the labs are running. And they are. Cool. One brain. Doing it all, everything. So, and you can of course just keep on adding more and more of these followers as you want and continue to stack them. Just make sure that you set, again, the inputs exactly correct. You set them all up here. Connect the greens and the reds, and that's it. So that is it in practice. So the next thing that probably matters is, all right, what were the benchmarks for this whole thing? Like, this thing is damn complicated. Like, shouldn't you actually go and prove that this thing is worthwhile? Well, yeah, I've ran benchmarks. I ran 380 of them to kind of prove that this is actually useful. So let's go talk through those. Okay, so these are the benchmarks and the files and the way that I've set them up. For all of these, the way that this works is I have 4,096 labs that are going to be currently running. And mainly just because this is incredibly beautiful to look at, I just wanted to show this. So they all are now offset. All their inserters, I've painstakingly wired them all up. And for all of the baseline benchmarks, I'm running everything with quality 1. And so all the different control methods. So this is the one that I have demonstrated. And the way that this works is I have now extracted this to 4,096 labs, and we're producing a casual 20 million signs per minute. So the question and the main thing that really mattered for me was the following. I wanted to make sure that if I press F5, that the entire number of labs is consistently at 4,096. All the tests need to have that condition in order for this whole test to be relevant. So I have that set up. I also am requesting things with agriculture science. Now I'm using superbots here for that, but that's also completely fine for the purpose of this demonstration. I want to kind of rule out the bot travel time, but I still want to include them because that's how all the tests are going to work. So this is one brain beating or controlling 4,095 labs. So I have then set this up, and I'll show just another one just while we're at it. So there are now going to be a whole bunch of different versions, and I have set them up for explosives, steel prod, bot speed, and research productivity. And I have ones where it uses just the wake lists purely, has no control logic. I have ones where they are going to be using the desync method that I talked about, and also a synchronous method. So let me go and show the sync method for this one. So in this one, the difference is that the benchmark is running all of the labs, but it has the same clock, but the difference is that the offsets are all set to happen at the same time. So that basically creates this giant pulse of all the inserters activating at the exact same time, rather than the rainbow wave that you saw before. So that was kind of an example where I wanted to make sure that, okay, is it actually worth separating them out or not? Finally, I also have a version that is going to be using bulk inserters. And then I also have one that is, just wake lists like I talked about. And finally, one that's running Q2. So for the uncommon science, I included everything is uncommon except for Promethium and agriculture science. The rest are all uncommon. And that is using the desync version, or the one where they have all the inserters staggered. So I set up a benchmark, and all of these are going to, and technically I was experimenting with this. This is actually 10 runs, and you'll see that here when I show it. But it's 10 runs for 3,600 ticks for all of the different files that I have here. So that means, and I have broken them down by running them based on just quality 1, synchronously, desynchronously using that desync method that I talked about before, steel productivity alone, bot speed by itself, explosives by itself, and research prod. And then I've dumped them all using this wonderful tool that Blousy has created. I have now automatically could just run this overnight and shove them all into these individual folders here. So let's go and talk about the first one. So let's go and compare the synchronous methods that we have. So here you can see all the different benchmarks, all their timing. So there's a total of 80. So there's actually well over 350 or I think 360 benchmarks that were run for this. So sorry to my computer, but let's go and talk about the results for the first one. So like just comparing using synchronous versus desynchronous in general, like which one is better. So you can see here for the steel productivity, it was interesting. They wound up being about the same, but you can really see that the max frame time was significantly higher. And you see that across the board. All the sync methods get up to the 38 ms mark, whereas all of the desync methods, no matter what you're running, are all at least a third of that. So this is already substantially better because it just means it's going to smooth it out. Now, whether it actually makes an average UPS difference, it didn't really, at least here. It was actually slightly worse for some reason, but I'm going to call this margin of error because these are so close that it's basically effectively the same on average, but they wound up just overall basically the max update time was way better just comparing these two. I mean, just look at this, right? This is a third of the max update time. So that means also your frame rate's going to be a little bit more stable in general. So the next one that was interesting was like looking at bot speed here. And these are all completely combined. So just sorry for that. But it was interesting to see that the desync method for bot speed, or even more so, the desync method for research prod, was better than the synchronous method for bot speed. And bot speed is only running 7 sciences, right? So that already shows that like that makes a pretty big improvement compared to the other one. And then the same thing, research prod, there was an improvement, and also for explosives, not as much. And it's interesting to me that my designs are just overall doing so much worse with explosives, and it might just be because I'm running agriculture science at just twice the rate. So maybe if you get your overall freshness up, then that would be better, but still, that's kind of the concessions that I've made. So we'll see once I actually deploy it in my real base. By the way, I'm not doing that for this video. This video is going to be long enough explaining this. Over the next week, my plan is to go and actually implement this in my base and actually do real testing. So otherwise, though, you can kind of see too that it was interesting to me that I had these random outliers for desync, so maybe I should have run this again. I don't know if I was doing something on my computer. Usually I don't touch anything, but it's interesting that it had this much of a variance compared to the synchronous method. So that's basically it. So that already shows that, yeah, it was definitely worth it to desync the inserters. That already made a huge difference. So next, let's talk about, I'll leave quality for the end. Let's talk about here. Let's switch over to the results for this, and I'll open this bad boy back up. So let's talk about the steel productivity by itself. So we're going to include Q2 for this. And this is, this blew my mind at how much better this was. So again, reminder, so this is Q2, so take this with a grain of salt, because this is running it with a second quality, but same number of labs, remember that. So using just wakeless alone, we got 504 UPS with that setup. Adding a bulk inserter like we did in the last video, and setting the clock to an exact time, so 60 every 60 ticks, it runs to every 2 ticks. That was a slight improvement. So that's what I was currently running in my base before. And then there's a slight variation of that. So this was what most people were using beforehand, was just using bulk inserters and just setting them on a clock. So you can already see that makes an improvement. But oh boy, the moment that you introduce, and this again was reproduced that we just saw with steel productivity with the stack versus desync, this jumped up substantially, an additional almost 200 UPS compared to the bulk version. This is already better. And then, yeah, you add Q2 in there, that's like double the UPS. So, and this is actually, and I'm happy to finally have this result to show this, because this has been my assumption with quality 2, that the limiting factor for labs is the inserters. And so you benefit by 2x every single time you're having Q2 in there. Now, is that enough? I mean, it's a lot of inserters, so it can really matter having that many all active at the same time. So yeah, in my example, it's 4 times the amount that I'm going to use, but it still is showing the relative performance difference. I mean, just look at this difference in step-up functions. You're using just wake lists, then you're using just a clocked bulk inserter, then you get to using the synchronous or desynchronous methods, which are basically nominally the same. And then finally, going to Q2 is a huge jump up. So just looking at this, what is that in percent differences? Well, 60% improvement from bulk inserters on a clock. That makes a difference. 60% improvement from using this new control logic method that I've been talking about. And then if you bump that up to Q2 or beyond, I'm assuming this number is going to keep going up if you go to Q3 or Q4, etc., and get an extra doubling. So that's pretty massive. So that's already like, I'm super excited about this result. That's awesome. So the next ones, let's go and look at now, like, let's say we're going to compare and do the 7 science. So for this one, this is running bot speed. So for this one, similar story here. So you, again, same kind of setup, but now just for bot speed. So if we look at this, again, you see that huge step up once you go to Q2, and you saw not as much of an improvement, interestingly enough, and I don't know exactly why that is, but still, running right now, when I was running bot speed, it was interesting that the bulk inserters had a 50% improvement on them. And this also kind of makes sense to me. And the reason being because bulk inserters, when you just have a clock, you don't know which science is running. So now I'm thinking about it, this makes sense. You see a bigger improvement when you're running more sciences. So the closer you get to running full agriculture, like you're running research productivity, the better and better this clock for bulk inserters are. Except not for research productivity, because it's half the rate, so they're swinging twice the amount. So I'm assuming once we get back and look at research prod, that the bulk inserters again gonna have a big dip down. So as you go up in science, the bulk inserter on that clock works better. But this was interesting to me to see that the desync method worked so much better and gave us an additional amount of UPS here. So again, points to desync. Here, even better than steel, this is 67% better on Q1. And then a mind-blowing 150% better with quality 2. So, cool. So that seems to be good. All right. Let's do agriculture science. This is the one that I already had observed in the very first one here that it wasn't as good, so unfortunately, but let's go and talk through that one, make sure I have the right preview open. So I'm running basically explosives for this. So once again, Q2, definitely better. What's interesting to me though is that there isn't as much of a gain that you're getting from running Q1 with the new control logic for this, and something I have to revisit. And you're seeing also a lot more variance in this, and I don't know why the variance was there for these methods, but it's interesting that there's such a floating range, because sometimes they'd even be in the bulk explosive range like this, where they'd overlap. So chalk that up to testing. I don't know exactly, but it is interesting to kind of note this. But what does that really mean? So again, it's still showing this 60% improvement over the baseline. But then again, you're running a 7 science for this, so that's where the stacked sync, basically the bulk inserters actually wind up doing about as good. And it's actually interesting that the bulk inserters, because I'm assuming when they're interacting with the agriculture sciences, like maybe there's some optimization there, I'm not quite sure, but it wound up actually performing better than the synchronous method. So the desync still like overall won, because I'm assuming it had, let me go and check this. Yeah, your max update time on the bulk inserters was still really high. So just not spacing them out is what hurt it in the end. So still interesting. So, but it just means that there's some things to refine for explosives to get it to be better. All right, so for the last one, the big comparison. Let's compare everything against research productivity. Let's go and open that up. Make sure that we got research prod. All right. So we've included Q2 for this. If you just do wake lists, that's 268 UPS that we were getting on average. So about half of what we were seeing was steel prod. Then you go to bulk inserters, and that's already a big improvement. And it's interesting though, I'm assuming the percent differences is not going to be as much from what I had talked about before, but I'll see in a second. I forgot, I haven't looked at the results in a little bit. So then if you use the stack method, well, that's already an improvement there. And then desyncing it makes an even more of an improvement. And then Q2 gives you another jump up. So what does that mean in percent differences? So here's that distribution again of just using wake lists versus the new method of desyncing it with Q2. So again, this is kind of what I was expecting, and I'm excited about this. So I'm expecting at least a 2x improvement by running Q2, and which makes it probably worth it, because all those inserters are really utilizing constantly. They basically are having to check it. So like, yeah, here we saw only a 40% improvement from bulk inserters, and that kind of makes sense because they're running 2 times the speed, because unless you can detect that research productivity is running, you're running it too fast for the bulk inserters. Then here for the stack inserters here, when it was synchronized, that was 53%, and then desyncing it, again, consistently, we're getting over 60% improvement. So that's pretty awesome. So then if you go here and go to Q2, all right, you're 100% better. So again, though, comparing this method versus the old one, this is only about a 20% improvement over the original version that we had created with just a clocked bulk inserter. But that 20% is worthwhile, and it even propagates more once you get up to higher quality. So this is definitely working for research productivity and for the other different sciences. So I'm excited about that. The last thing is I wanted to do was just an overall comparison. And I've always run these benchmarks separately just to see if I can get consistent results again. So like, again, looking at this was over 80 tests. Each of these were individual runs. I didn't copy and paste the runs over. These are all just individual. So just to see if we can get the same results. So here, what's interesting now, and this was just showing kind of some of the variations in the test runs, when I ran the control comparison for quality, and this also makes sense just kind of as you go down. So steel prod's always going to be the best. Desyncing for Q2 was, and I did not do a synchronous version for Q2, this just to be clear. But again, all the desync versions, just looking at this here, these are all only desynchronized and just running it for that. So if you see that here, the results here are kind of showing exactly what I would expect. Running Q1 for desynchronized for steel productivity, you saw this amount, basically a 200 UPS improvement by just desyncing it, and going to Q2. So that's a pretty big one. Then, so compared to Q1, right? So then if you look at quality 2 for the bot speed compared to quality 1 for bot speed, that was a huge jump up, and it completely jumped through the other ones. And you can see here just kind of like, this is compared to this one for research products compared to this, and then explosives are down at the bottom. And so consistently, even though I improved Q2, now I didn't run Q2 for agriculture science and for Promethium science, just because I don't know if it's worth doing UPS wise, so I didn't include that. So that also hurts the numbers there to not get a full 2x improvement. But it leads me to continue to believe that the performance loss that I'm getting from these is because of the way that I'm controlling agriculture science. So I may revisit it. But right now, I'm already super stoked with the difference in these values, right? So you're just seeing, again, just like running Q2 versus Q1, huge jump up. Running the bot speed versus running the bot speed down here, right? And then research prod versus research prod, and Q1 versus Q2, and then again. So it's a pretty big difference. Now, this is a percent improvement is probably not that useful because it's just showing it compared to the worst one. But what we can really do is we can kind of just like normalize and average this, and you could say like, okay, this was basically running the explosives in Q2 was 33 points better than this, And then running research prod here was 35 points better than this, and so forth. And so you can see just kind of that same improvement kind of going across the board. So running Q2 is super worth it for labs. There is, like, in my mind, no doubt about it now that we have a better control method. And it also means that, yeah, I'm definitely going to be switching to this. So that, in a nutshell, is all the results. I'm going to clean all this up, and I'm going to then post a final README with hopefully a whole bunch of the explanations in this before the video comes out. So I'll have a link to this if you want to just do a readable version of this or refer back to it. I always put a readable version because my videos can be quite lengthy as I explain a lot of these concepts. And then you always have something that you can refer back to, or you could share the results and you can explain some of the things you see in this video. If you made it this far in the video, first of all, thank you for the attention span as I went through all of those inserters and all the logic that's involved in that. If you didn't and you skipped to the end and you just watched the actual results, also completely fine. Although the explanation is probably worth it if you ever need to debug it, so I'd highly recommend you go look at that. This has been about 3 weeks of me working with several people in my Discord group. Just a couple shout outs for people that were extremely helpful. So Conage was extremely helpful in explaining and figuring out a lot of like some of the random timings and some of the things, and just going back and forth with him was really helpful. Kira was also really helpful in some of the early on blueprints that were sent that helped with some of the like synchronous timings on all these different labs. So shout out to them as well. So, and then just, yeah, this has been a community project. I've gone definitely overboard with a lot of the extra control logic and things that I wound up coming up with. So we included shift registers in this video. We've included timers, separating inserters and splitting them up in time. We've done a whole bunch of things and relying on wake lists. And so someone in a previous video wound up saying this, they felt like this was the midterm and they were just applying all these things. This is definitely, this would be like your final exam, is kind of how I would have put it. So yeah, this was a lot of head scratching for the last 3 weeks trying to figure this out, but I'm really, really happy that I have a final, or at least a solution that really works for this. And I'm super proud of it. And plus, hey, it is going to look really cool, I'm assuming, when all of these LEDs are on in my actual base and are pulsating from the middle of where all the science gets inserted and goes to the outside. So super excited to actually implement it. But that is the conclusion of my, at least designing labs series, which will just be finalized by me actually putting it into my base. So I'm going to be doing that this next week. So stay tuned and subscribe for that. As always, thank you. Appreciate all the comments in the video. And have a fantastic day.